In this video, we'll cover Section 4 of Chapter 4 on quantitative variables and the normal distribution. We'll review the 68, 95, 99.7 rule. We'll talk more about the normal curve, and we'll talk about finding standardized z-scores. In the 4 stages of statistics, what we're talking about today will cover displaying and summarizing one quantitative variable. When we're talking about the distribution of a quantitative variable, there are 3 terms that we will often talk about. The shape of the distribution, which tells us which values tend to occur more frequently or less frequently. The center of the distribution, and the spread of the distribution, which talks about how far away a typical value for the variable is from the center. Today we're going to focus on 2 aspects in particular: the mean as a measure of the center, which is the arithmetic average of the values, and the standard deviation, a measure of the spread, which tells you how far typically a number is from the mean. To review, the 68, 95, 99.7 rule tells us that when we have a normally distributed variable, then of the values, 68% of them approximately will be within 1 standard deviation of the mean. 95% will be within 2 standard deviations of the mean, and 99.7% will be within 3 standard deviations of the mean. Here's a picture of what a typical histogram would look like. When we're talking about whether a value is unusual or not, we'll often consider 2 standard deviations to be the cutoff. If a value is more than 2 standard deviations away from the mean, either above or below, we'll consider that to be unusual. And remember that as the number of values that we consider goes up toward infinity, the histogram will tend to follow along the normal curve. And another reminder about notation. If we're looking at a sample, not a population, but a sample, we'll indicate the statistics that we're interested in with an X bar for the mean and an S for the standard deviation. If our values represent a population, we'll use the Greek letter mu for the mean and sigma for the standard deviation. On our histogram, you can see that X bar, the mean, is in the middle, and S, the standard deviation, tells you how far away 68% of the values tend to be. As we move to the population, mu is in the middle, and sigma indicates the spread. For example, if adult male foot lengths are normally distributed with mean 11 and standard deviation of 1.5, and we take a sample of 9 people who have foot lengths with mean 11.2 and standard deviation 1.7, what notation do we use for the sample, and what notation do we use for the population? We're given a population with mean 11 and standard deviation 1.5, and a sample with mean 11.2 and standard deviation 1.7. So we'll say X bar is 11.2 and S is 1.7, and we'll say mu is 11 and sigma is 1.5. So how do we display this? Here's our normal curve. We're looking at the population, so using the curve is appropriate. The mean is 11, the standard deviation is 1.5. So what we'll do is we'll label the middle of the distribution mu, right in the middle, the 11, and we'll count out by standard deviations. We'll go up and down by 1.5 to give us 12.5 and 9.5. We'll go up and down by another standard deviation to give us 14 and 8, and we'll go up and down by yet another standard deviation to give us 6.5 and 15.5. Sometimes we want to be careful about not applying the rule. If we consider, for example, the ages of all undergrads at a university with mean 20.5 and standard deviation 2.9 years, how would we display the ages? Since there will be some older people enrolled in a university, we would expect there to be some high outliers, which would skew the distribution to the right. Since we don't expect this to be a normal curve, we would not sketch it with the normal curve, and we would not apply the 68, 95, 99.7 rule. Since we don't know exactly what the data points are, we don't have enough to sketch the curve. Let's talk about standard values. When we measure the distance from the mean of a particular value in standard deviations, the process is called standardizing. For example, if we're looking at the ages of mothers when giving birth, those ages are distributed approximately normally. The mean is 27 and the standard deviation is 6. If we have two mothers, one age 35 and one age 43, are those considered unusually old? Certainly both are above the mean, so we would expect them to have a positive z-score. Let's compute them. Age 35, to standardize, we subtract the mean and divide by the standard deviation, which gives us 1.33 standard deviations above the mean. Is that unusually old? Remember that our cutoff for being unusual is about 2 standard deviations. 1.33 is smaller than 2, so no, this is not unusually old. Age 43, however, when we subtract the mean and divide by 6, we get 2.67. That's well above 2, so we would say that is unusually old. So let's define z-score. The z-score, or the standardized value, tells how many standard deviations below or above the mean the original x value is. So z is the actual value minus the mean in the numerator, all divided by the standard deviation. If we're looking at a sample, that means z is equal to x minus x bar, all divided by s. In a population, we'll use mu and sigma for the mean and standard deviation. If you're given a z-score and you wish to find the actual value, all we need to do is solve that original equation that we see above. We take the z-score, multiply by the standard deviation, and add the mean. So looking at the empirical rule, the 98, 95, 99.7 rule, in the context of z-scores, what does that rule tell us? Well, first let's take our distribution, sketch the curve, label the mean as 0 and the standard deviation as 1. Then we know that 68% of our data values will be between -1 and +1, 95% would be between -2 and +2, and 99.7% would be between -3 and +3. Let's look at how to do some of these computations using our calculators. Your calculator may look a little bit different from this, but the procedure is the same pretty much on all of them. Let's start by finding the area underneath the normal curve between z-scores of -0.75 and +0.5. To do this, we'll go into our distribution menu and we'll select normal CDF. Normal PDF is something that we will never use. So I'm going to push 2 to select normal CDF. If there's something already filled in for the lower value, it's probably -1 times 10 to the 99th, which is the calculator's way of saying negative infinity. We don't want to go that far down. We want -0.75. So I will type -0.75. For the upper value, we want 1/2, 0.5. The mean and the standard deviation we'll leave as 0 and 1. If we weren't given the z-scores, we had actual values. We could type in the actual values for the lower and upper, and then enter our mean and our standard deviation next to mu and sigma. When I push enter, it pastes in the formula that the calculator uses to compute that area, and I push enter, and it tells me the area is 0.464. That's about 46%. If you'd like to see what that looks like on the graph of the distribution, we can do that. But before we do, push the window button to go in and edit these settings. To get a good picture of the normal distribution, I recommend using an x minimum value of negative 3.5, an x maximum value of 3.5, and a scale of 1 works. For the minimum y value, let's use, that's the wrong button. Let's go back, delete that. Let's use negative 0.25 and a y maximum of 0.5. We don't need the scale on the y-axis. That's not as important to us. If you want to change the y scale, you're welcome to. Now that we've got our window fixed, let's go back to the distribution menu. And this time, instead of choosing something under distribution, let's go over to draw. And let's choose shade norm. Let's enter our values again. Negative 0.75 for the lower bound, 0.5 for the upper bound, and again we have a mean of 0 and a standard deviation of 1. I'll select draw, and then on the graph you see the normal distribution, and you see the area that we were looking for in question, which then gets reported. Now let's say that we want to find a z-score given an area. So let's say that we want to know how much of our data is below a z-score of 1.3. To do that, we'll go back to the distribution. I think I misspoke. I apologize. Let's say that we're given an area under the distribution of, let's say, 70%. What z-score corresponds to that 70th percentile? For that, we'll use inverse norm. Inverse norm is always what we use when we're given an area and we wish to find the z-score. I want to know the z-score that corresponds to an area of 0.7, that's 70%, and I push enter. I get a z-score of 0.52. That means 70% of the data would be to the left of a z-score of 0.52. Let's use Excel to do some of the computations that we've been looking at. Remember, if you've got a set of data and you wish to compute the mean, here I've taken some of the heights from the student survey data. We don't need them all, this is just a selection. We need to insert a formula. So I'm going to select the Formulas tab at the top. Under More Functions and Statistical, I see Average. And if you hold your cursor over there, you see it tells you it's the arithmetic mean, and that's what we're looking for. So I'm going to select that. The numbers that I want, I'm going to choose my little button there to minimize that. I'm going to go over and drag over the numbers I want to find the mean for. I'll expand it back out. Notice it reports the mean here. I'll click OK, and there, let me label it as our mean. Now for the standard deviation, I'll go back into Functions, Statistical, and I'll scroll down until I see something that looks like standard deviation. And there are two of them, STDEVP and STDEVS. The first one is for the population. The second one is for a sample. Since this is a sample, I will choose the latter. I'll click the button besides number 1 to minimize this window, and I'll select our data again. And I'll click OK. Our standard deviation is 4.16. So let's say we have a student whose actual value is 72 inches. What's the z-score? To find the z-score, remember we need a formula. We take the actual value, we subtract the mean, and we divide by the standard deviation. Since this is going to be a formula, I'll start by typing the equal symbol. The numerator needs to go in parentheses, so I'll start with parentheses. And this is going to be equal to the actual value, which is entered here. I'm just going to click there to enter the value from that cell. I'll click minus. And then I want to subtract the mean, so I'll click in the cell that has the mean. I'll close the parentheses, and I want that divided by the standard deviation. I'll click on the standard deviation to enter that. And I push enter, and that gives us a z-score of 1.31. Now, how do we use the normal distribution in Excel? The normal distribution is also found under More Functions, Statistical. And as we scroll down, we'll see several options for norm. Norm.dist, which returns the normal distribution for the specified mean and standard deviation. We'll talk about what that means in a second. Inverse norm, which means that what it did for the on our calculators. Norm S distribution and norm S inverse are for the standard distribution. In other words, if you have things as z-scores already. If you already have z-scores, you want to use the one with the S in it. If you don't already have z-scores, we'll use the one without the S in it. Let's work with z-scores. Let's say we want to know the area between z equals negative 0.2 and z equals positive 1.3. Maybe make this a little bit bigger so you can see it better. All right, since I want an area, I'm going to go under More Functions, Statistical. I'll go down to Norm. We got z-score, so I'll use the norm with the S in it, and I want the distribution. Now, unlike with the calculator, this only asks us for the z-score. I've got 2 z-scores. So what do I do? Well, what I'm going to do is start by putting in the lower value, negative 0.2. And for cumulative, we're always going to want true. So I'll type in true in all caps. When I hit enter, what gets reported is the area to the left of z equals negative 0.2. That's not the area we want. We want the area between negative 0.2 and 1.3. So now let's find the area to the left of 1.3 using the same procedure we used a moment ago. Let's go down to norm distribution with the S in it. I'll use a z value of 1.3. Whoops, I hit enter too quickly. Let me delete that. Do it again. I forgot to enter true. So let's go back to statistical. Norm S distribution. Z-score is 1.3. Cumulative is true. And I see that the area to the left of z equals 1.3 is 90.3%. So now what is the area in between? To find that, we simply subtract. The area between is equal to that larger number minus the smaller number. 0.482459, that's 48.2%. Now let's find the z-score that corresponds to the, let's say, 65th percentile. Here we'll go under more functions again, statistical. Since we're given an area, I want to know the z-score that corresponds to the point at which there's 65% of the area under the curve to the left of that z-score. We'll use inverse norm. I'll use the S since this is a z-score we're looking for. And here I enter the probability. Here it says probability, but what it really means is proportion, and that's 0.65. And we see that a z-score of 0.385 corresponds to the 65th percentile. So, if we're looking at exam scores that are normally distributed, let's say we have two students whose z-scores are minus 0.4 and positive 1.5. How are those interpreted? The first one, minus 0.4, is below average. I know it's below average because it's negative. But it's not too far below average, so it's not awful. Positive 1.5 would be between the top 16%, which is how big the tail is to the right of 1, and the top 2.5%, which is how much area is in the tail to the right of 2. So a score of positive 1.5 is between the top 16% and the top 2.5%, which is pretty good, but not among the top scores in the class. Let's look at a table to help us interpret z-scores. This table indicates how unusual a value of z is by looking at its absolute value. Remember, the absolute value of a number is an indication of how far it is from 0. Since these are z-scores, 0 is the mean. So if the absolute value of z is greater than 3, that means that z is not in the middle 99.7% of the data, which, remember, 99.7% of the data is within 3 standard deviations of the mean. So if the absolute value of z is greater than 3, that z-score is among the 0.3% most unusual scores we see. That's extremely unusual. If the absolute value of z is between 2 and 3, we'll call that very unusual. If the absolute value of z is between 1.75 and 2, that's unusual. Remember, 2 is our cutoff for being unusual. You can read the rest of the interpretations below. Let's look at an example. IQ scores are normal with mean of 100 and standard deviation of 15. In 2002, the Supreme Court ruled that execution of the mentally retarded is cruel and unusual punishment, which is in violation of the 8th Amendment of the Constitution. A convicted criminal's IQ is 59. Is that borderline or well below the cutoff, which is z equals -2, for mental retardation? Is the death penalty appropriate for this criminal? Computing the z-score, we subtract the mean from 59 and divide by 15, which gives us negative 2.73. That's far below the cutoff of -2, so the death penalty would be inappropriate. Let's look at another example of unstandardizing. Again, considering IQs, mean is 100, standard deviation is 15. If a person's z-score is positive 1.2, then what is that student's IQ? To compute it, we take the z-score, 1.2, we multiply it by the standard deviation, which is 15, and then we add the mean. That gives us 118. To review, the z-score, or the standardized value, is a measure of how many standard deviations above or below the mean the original value is. To compute z, we take the observed value, we subtract the mean, keeping in mind if we're looking at a sample, we'll subtract x bar. If we're looking at a population, we'll subtract mu, and then divide that result by the standard deviation, s for a sample and sigma for a population. If you're given a z-score and you want to find the original x, take the z-score, multiply by the standard deviation, and add the mean. Here's an example. If an exam has mean of 79 and a standard deviation of 5, a student's reported z-score is minus 0.4. What's the student's original score? Here we're given the z-score. We wish to find the actual score, so we'll take the score, the z-score, multiply it by the standard deviation, and add the mean. That gives us an original score of 77. Remember that if a z-score is negative, that means the original value x is below average. Here's another example. In the student survey data, students' computer times have a mean of 97.9 and a standard deviation of 109.7. How do we know just from this information that the distribution is not normal? Remember, the empirical rule tells us that 68% of the data should be within one standard deviation of the mean. That means 32% of the data would be outside of one standard deviation from the mean, and the normal distribution is symmetric. So the left-hand tail and the right-hand tail should have the same area. That means that 16% of our data should be below one standard deviation below the mean. One standard deviation below the mean takes us to negative 11.8 minutes. There's no way that 16% of the data are below that because the times have to be positive. So I'm certain that this distribution is not normal. In fact, it must be very strongly skewed to the right. In this video, we talked about normal distributions. We talked about the notation that we use for a sample versus the notation for a population. We talked about how to standardize a score by taking the actual value, subtracting the mean, and taking the result and dividing by the standard deviation. We looked at how the 68, 95, 99.7 rule applies to standardized scores. We talked about how to interpret a standardized score and how to unstandardize a score by taking the z-score, multiplying by the standard deviation, and adding the mean.